Guys, welcome back to my channel. So today we're going to be talking about graphing conics, and we're just going to focus on quick sketches without using technology, just trying to quickly recognize what the general idea for these are going to be and not necessarily going super in detail, just quick sketches. So as a reminder what our four conics are that we're going to be studying, we have the circles, the ellipses, the hyperbolas, and the parabolas. So hopefully you've seen the other video that explains how the different slices will form the different conic sections, and you've seen some of these names before. We're going to focus just on sketching them. So let's take a look at this formula. I can notice right away that I don't have equals 1. If I wanted to get an equals 1, I could divide both sides by 4. And I would end up getting x minus 5 squared over 4 plus y minus 2 squared over 4 equals to 1. And I can recognize that that is a circle. Some people don't bother to do that step, so it's definitely optional. It's just a matter of if you recognize that it's a circle, what is it that's going to distinguish this as a circle versus an ellipse is that I have a 4 under both my x and y terms. The x and y's are both squared, and it's positive. So I can see that I have a circle, and the center of the circle is going to be important for graphing it. So the center of a circle is what's going to make the x and the y squared terms 0. So it would be the coordinates 5, 2. And the radius is going to be the square root of that 4, the number that was originally on the right-hand side, which is 2. So our radius is 2. Okay, so when we graph a circle, I feel like most of us have seen in geometry, the basic idea is you start with the center and you have your radius, and if you had a fancy tool like a protractor or a compass, you could graph the circle perfectly using just the center and radius. So that's the general idea for how we'll do it. So counting in the x direction, 1, 2, 3, 4, 5, and then up 2. Here's my center for the circle, and my radius is 2, so I'll go 2 in all 4 directions. There we go. Now these are actually the points that I'm bolding right now are going to be the points that are actually on the circle. Okay. So let's move on to a different conic. Okay, so let's go through our process of elimination on this one. I see that I have my equals 1 here, and I have a 4 and a 9, different numbers under my x and y squared terms. So it's not going to be a circle. I notice that x term and y term are both squared, so it's not a parabola. And I have both terms positive, so that would be an ellipse. For the ellipse, we're going to need the center, which is again what makes the x and y terms 0. So just the part that's being squared would be 0 if x was 1 and y is 0. And then what is going to be the case for an ellipse is that instead of having a radius that extends in all 4 directions, you can kind of think of it as having like a horizontal axis and a vertical axis. So the horizontal axis length is going to be decided based on the square root of the number under the x. So the horizontal, we're going to be counting 2 units left and right from the center. Okay, and our vertical is 9, so the square root of 9 is 3, so that means we're going to be counting 3 units up and down from the center. Okay, and that's enough information to get our sketch going. Okay, so our center is at 1, 0. And we're going to be counting 2 units left and right. We're going to be counting 3 units up and down. And then those are the points that are on the ellipse. Actually, those 4 points that I just graphed. I'm not so slick on ellipses because I don't have an automatic ellipse predictor tool here for my stylus. Doing my best though to make it look like both sides are supposed to be symmetric. And then let's label our axes, x and y. And our center is 1, 0. So our points that are actually on the ellipse would be 1, 3, and those are my 4 points that are actually on the ellipse. Okay. So just scrolling up to see where each part of the formula went. You see how it all goes together there? Okay, let's move on to the next one. Okay, so let's go through our process of elimination for this one. I see x and y are both squared, so it's not going to be a parabola. I see different numbers under the x and y squared terms, so it's not a circle. And more importantly, I see a negative on one of the terms. So this is definitely going to be a hyperbola. It's the only one with a negative in terms of conic sections. So, well, in terms of conic sections that have both terms squared, I should say, you can definitely have a negative for a parabola. Okay, so let's take a look at what our center would be. The center for a hyperbola is going to be what makes the x and y squared term 0. So it'll be center 0, negative 1. Now instead of having axes, we're going to have it's going to be like a rectangle. And the rectangle is going to be used to generate asymptotes. And the hyperbola is either going to open on the top and bottom branches or the left and right branches. And it's going to depend on which term is positive. So I notice that my x term is the positive term. So this is going to be a left-right hyperbola. Okay. And in the x direction, it's going to be, we're counting out 4 units. And in the up and down vertical direction, it's going to be 3 units. Okay, so let's get this start of the box down. So the center is 0, negative 1. We're counting 3 in the vertical. And we're counting 4 in the horizontal. Okay, so now we're going to use this to form our rectangle. So I'm going to form a rectangle by connecting the diagonals. Okay, so sometimes you'll see people actually dash out the box, but dashing out the box is optional. It's whatever is going to help you visualize what's going on. I generally do, just so that we can see what we're connecting. So then the actual asymptotes for the hyperbola are the diagonals of this rectangle that we just blocked out. So there's my asymptotes. So just kind of identifying that these are supposed to be dashed. Okay, let's write the formula for these asymptotes now that we've got them looking sufficiently dashed. So the formula would be, we need the slope and we need a point that's on the asymptote. So we're going to use point slope, and remember the formula for point slope is you do x minus your x coordinate on the line equals your slope. It is the slope times x minus the x coordinate equals y minus the y coordinate. So filling in our values, our slope for this line that's going up is going to be from left to right. It looks like we're gaining, rising 1, 2, 3. So up 3 across 1, 2, 3, 4. So the slope would be 3/4. And x minus the x coordinate, the point on this would be the center. I'm bolding out, so the center x coordinate is 0. And then the y coordinate for that is -1, so y minus -1 is y plus 1. Okay, so there's our formula for that asymptote. The formula for the asymptote on the bottom, the only thing that's different is that it's a negative slope. So still contains the same center point. So there's our formula for the asymptotes. And then the only other formula that we might want is the formula for the focus. So the focus is going to be important if you were trying to super formally construct the hyperbola. We're not really doing that. We're doing a quick sketch because when we're doing this kind of thing later on, we're probably trying to just get a quick picture and not necessarily get the most exact construction, but it might be useful at some point. So we'll write down the focus formula, and to find the focal length, it's going to be, the focal length is c, and it's the square root of a squared plus b squared. So for us, the a squared was what was under the x, 16. The b squared is what's under the y. So it's going to be the square root of 16 plus 9. So root 25. So c is 5. Okay, so then we count 5 out from the center, left and right, because this is a left and right hyperbola. So there's our focus. There's our focus. And then our actual point on the hyperbola, the local extrema of the hyperbola will be the little bottoms of the bowl, and the actual branches open up to try and lay alongside the asymptotes. Okay, and I did my best to make both sides look symmetric. They're supposed to be the same exact shape. I did not do, obviously, a perfect job. But notice how the focus lays along the line of the center, and it lays along the line of the branches. So the focus is inside the actual branches themselves. Okay, so there's a hyperbola. I think this one's by far the hardest to sketch. For this next example, it looks like we're going to be looking at, based on our pattern recognition, we have one variable squared and the other variable not squared, so this has to be a parabola. Now the question is left to right or up and down. So I can see that the y is squared, so this is going to be a left, right, and we need to know which direction it opens. So I'm going to go to my side of the equation that has a non-squared term, and I notice that I have the coefficient is positive. So because it's a positive, it means we're going to open to the right. Okay, so this is a right opening parabola. Now we need to know the vertex. So the vertex is what makes my x and y arguments 0. So it would be -1 for the x coordinate and 2 for the y coordinate. Okay, now the other thing we definitely do need for our parabola is we do need to know the focal length. So the focal length, let me highlight where that's going to come into play. The focal length is the number that's directly in front of the non-squared term. So the coefficient of our x term here is going to give us our focal length. Now the focal length is going to be take whatever number you see and divide by 4. So the number that I see is 4, I divide it by 4, I get focal length 1. So now to get the equations for everything else, I'm going to actually wait until I have a sketch and then generate my equations if I need them from there. So my vertex is -1, 2, and I'm opening to the right, so my focus is going to be to the right by, it was 1 unit, so 1 unit from the vertex. In the opposite direction lies my directrix, which is a line that is used to formally construct the parabola. Sometimes it might be relevant, so we're just going to get that on the sketch so we know where it is. And then we're going to need to know, like, how narrow is this parabola, how wide is this parabola. That's controlled by the lattice rectum, which the lattice rectum length is total, that 4 units is going to be total 4 units. So split evenly, it's going to be 2 up and 2 down from my focus. So at the end of that line segment that we just formed, that is a lattice rectum. The endpoints are actually on the parabola. Okay. So you'll notice that the cool thing about a parabola, this one, we did not definitely do a formal construction and get it drawn, but we can kind of see the construction on it a little bit. You notice that the length from here to here is the same as the length from here to here. Notice that the length from here to here is the length. So if I look at a point, the distance from the point on the parabola to the focus is the same as the length to the directrix. If I just drop it down vertically. Okay. So those are all of our conic sections. And again, this was by no means supposed to be a thorough study. We're just kind of going over a quick sketch technique that I like to use. I'm very much not doing these beautiful conics their full justice. If you would like to see some more in-depth detail about formal constructions, I'll go ahead and link you to some videos that I like below to do that. See you next time.